In this section, we're going to talk about the derivative as a function. So here is a definition of the derivative. We're going to have a function f. The derivative of that function is denoted by f prime. That's f prime. Is the function whose domain consists of those values of x such that the following limit exists. So for our f prime, or our derivative, f prime of x equals the limit of our function f x plus h minus f of x divided by h as h approaches 0. A function is said to be differentiable at a if f prime of a exists. More generally, a function is said to be differentiable on S, which is a set, if it's differentiable at every point in an open set S. And a differentiable function is one in which f prime of x exists on its domain. So let's look at a function here. Here we have f of x equals x cubed. We're going to estimate it by we're going to use the calculators here, and we're going to find the average rate of change of the secant line, or the slope of the secant line. So that's what our m secant here. We're going to use that, and we're going to see if there's a pattern. So we're going to put our function in. So here's our L1, L2, L3, L4, L5, L6, and here's the values we get. And so we're going to plug them in here, and that's going to give us our slope, or our average rate of change. Okay, so as we notice when we do 1, so let's look at what we have here. We have y, so y1, L1 plus 1, so that would be 2, and we're going to cube it, so that would give us 8, minus, well, if I put L1 in, which is 1, that gives us 1, and that's going to be 7 on top, divided by, and this is going to end up being 1, so we end up with 7. All right, and so we're going to do that. We're looking at all of those, in which our calculator is giving these to us. So, have you noticed a pattern here? Here we got 1 to 2, 2 to 3, 3 to 4, 4 to 5, 5 to 6, 6 to 7. So the pattern of the average rates looks quadratic. So we can see as it goes up of the average rate of changes, it looks quadratic. So our derivative of this function is 3x squared. Well, there it is. That's a quadratic. So we can see that it's a function, okay, and it's the derivative function. It's the derivative of x cubed is 3x squared, which is also a function. It's the derivative function. So how do we interpret the derivative? Well, we can interpret it in two ways. The slope of the tangent line to the graph of a function at a given x value. The rate of change of the function with respect to the independent variable x at a given x values. So slope, rate of change, it's at a particular point, or an instantaneous rate of change. To find the derivative, we change our naming procedure of points that the secant line goes through. We call the first x value x, and the second one h plus h, x plus h, if I can talk. Thus, here we have our definition of a derivative, and it's the limit as h approaches 0 of our difference quotient, which is f of x plus h minus f of x divided by h. And here you can see kind of a picture view. Here is x, and then we add h, whatever that value is, to it. So this is my x plus h. H is that distance, how far away from x we are. And then we have f of x for my x, and then my f of x plus h, and there's our 2 points, and that is the secant line if we connect those 2 dots there, or those 2 points. All right, so let's look at an example We want to find the derivative using this particular definition of a derivative, the limit of a difference quotient. And so what we do, here we have our difference quotient, which is f prime of x, and we're going to plug in wherever our function has an x, we're going to put x plus h. So I have negative 3, x plus h, there's that x squared, minus 5, x plus h plus 1. That is all of this f of x plus h, minus the function, which is negative 3x squared minus 5x plus 1. All of that's over h. Then we're going to simplify by multiplying everything out. So we're going to multiply this binomial, distribute the 3, distribute the 5. There's negative 5x minus 5h plus, and then a negative of negative 3x squared gives us a positive 5x minus 1. And what's nice here, a lot cancels. This 5x and negative 5x cancels out. Our negative 3x squared and our positive 3x squared cancels out. And we're left with, and then we can do our 1 and negative 1 cancel. So we're left with this negative 6hx minus 3h squared minus 5h all over h. The limit, don't forget your limit here, because we haven't taken the limit yet. We're going to look at that here in a minute. Then I can factor out an h, which is nice, cancel these out. And my derivative of this particular function is negative 6x minus 5, because when I take the limit here, substitute 0 in, my negative 3h cancels out, that becomes 0, and I'm left with negative 6x minus 5. And so here you can see the graph of the original function, and then the derivative is a line. And you notice these are one less power. Just like when we looked at the derivative of the x cubed, it ended up being an x squared, so it's one less power. And they're all functions, a derivative function and a function. All right, let's look at another example. What about finding the derivative of a square root function? And we're going to use our limit of a difference quotient, and it's the same procedure. Wherever I have an x, I'm going to put x plus h minus the function, which is square root of x over h. Now, how do I simplify this? We could try taking the limit, but of course, this gives us 0 in the denominator, which is undefined, so we're going to have to simplify it. Here's where we use those conjugates to simplify the limit. And so when I multiply these conjugates together, remember the middle terms will cancel out. So square root of x plus h times square root of x plus h gives me x plus h. And then the square root of x times the square root of x is going to be x minus, and those middle terms cancel. And we're just going to leave this like this right at the moment, because what happens, these x's cancel out. I'm left with just an h. These h's will cancel, and we can put our 0. Now we can do the limit of this, which will give me square root of x plus square root of x. And there is our f prime of x is 1 over 2 square root of x. And again, I like that you can look at the graphs here. Here is the square root of x. And then here's a picture of its derivative. Okay. So again, and again, if you take 1/2 minus 1, that gives you x to the negative 1/2, which would be this function. So it's still one less as far as the power. And we can look at the functions, the functional graphs. Let's look at some notations. Notations to express the derivative. So it's kind of neat. We have notations and notions. We use a variety of different notations to express the derivative. So you may see a variety of these depending on where you're studying or what textbook you're using. So f prime is always a very popular, f prime of x, g prime of x, using the prime. Could be y prime, dy dx, change in y, we're changing x, df dx, d dx. So these are all different notations. And then again, you can look at f prime of 3, and they're just showing how if you're actually going to evaluate the derivatives at a certain point where x equals 3, this is what that would look like. You see we get the same answer. dy dx, if it's this notation, you would see x equals 3. That's what we're evaluating it at, and so on. So these are just different notations and some notions of a derivative. Is it's a rate of change. It can be a marginal could be a marginal profit, marginal cost. Those are all derivatives, and so those are different notions of derivatives out there. The dy dx notation is called the Leibniz notation, and it's very common, especially in engineering and physics. So this is one you'd want to get familiar with. When we're talking about the change in y and change in x, the change in y is the difference in the y values, which should make sense. It's the difference of the y values. We do this with slope, been doing it for quite a while. And then we have change in x or delta x. This is delta y, delta x, change in y over change in x. The derivative, which can be thought of as an instantaneous rate of change, there's another notion, instantaneous rate of change, with respect, change of y with respect to x. And this is how it is expressed, dy dx, which equals the limit of the change in y over change in x. So it's again, notation is important. You need to understand what notation you're using and what they mean. And again, here's that change in x, the difference, change in y, the difference of the y values here.